Okay, so we have been talking about the predictive coding, and the last thing that we saw was not the derivation, because it takes too long time to explain the derivations, but the algorithm, which gives an iterative way of developing the predictive filter coefficients, linear predictive filter coefficients, by an updating procedure. And the methodology also gives you the values in an iterative manner again, the values of the prediction error, expected prediction error. But we didn't do an example for that one. So I will start by doing one example, and then I will continue with with some other aspects of predictive coding. The example that I will show you is, let's make it black, is as follows. Suppose that we made some measurements of the autocorrelation values, and they are found out to be like Rx of 0 is 1, Rx of 1 is equal to 0.5, Rx of 2 is equal to also 0.5, and Rx of 3, sorry, Rx of 3 is 0.25, which is 1 over 4. So we have these autocorrelation values. I didn't check whether they are legitimate or available autocorrelation values or not. As we all know, the Fourier transform of this sequence is supposed to be always positive. Is it always positive? You have to assume that Rx of -1 is 0.5, Rx of -2 is 0.5, and Rx of -3 is 0.25 too. So it's like a decreasing shape. I don't know if its Fourier transform gives you all positive values, but anyway, that's not our problem right now. We are going to solve the so-called Levinson-Durbin recursion formula. That was the recursive or the iterative way of solving the linear filter coefficients. We will start the Levinson-Durbin recursion from the first coefficient, which will be A1 of 1, and that is the negative of the first order linear filter coefficient. And the linear filter coefficient, as we all know, is R1 over R0. So this is the negative of it, minus Rx1 over Rx0. And that will give you minus 1 over 2, 0.5 over 1, in other words. And the squared error with this case, for this case, is, by the way, this is also K1. 1 minus K1 square times Rx of 0. So if you substitute K1 is equal to minus 1 over 2, 1 minus 1 over 2 square times 1 will give you 3 over 4. So we now know that the filter coefficients are, the only filter coefficient is 1 over 2, and it makes a prediction error of 3 over 4, which is slightly less than 1, but not really a lot less than 1. And that's an interesting observation. The original variance of the signal was already 1, and after making predictions with this kind of a system, it can only become 3 over 4, which is slightly less than 1, but not very good, right? So we now come up with an A1 vector, which consists of 1 and minus 1 over 2, and sigma d1 square is equal to 3 over 4. So how do we proceed to the second order predictor. We proceed like this. We evaluate K2, which will now be equal to A22, but A12 will be different. We will see what it becomes. From the formula, as we see, K1 is here, and now we are looking for what is K2. That's equal to minus Rx2 minus A11, which we already found to be 1 over 2, minus 1 over 2, times Rx1 over the previous variance. Now, this term that you are seeing here is essentially the multiplication of an inverted way of looking at this A1, okay, making it flipped, and it is then multiplying Rx1, Rx2 composition of another vector. So this is a vector-vector multiplication, and that's why we are having a summation of terms by means of scaling. When you see the third iteration, probably you will better understand how to proceed with this kind of situation. And this one, by the way, if you just substitute the values inside the equation, you will find it to be equal to minus 1 over 3. So the second filter coefficient will be 1 over 3, the negative of this one. K2 is A2, 2. So that would actually be the second of A2. But it will be equal to 1 over 3, so the coefficient is 1 over 3. But the previous coefficient, which was already 1 over 2, will also be updated. So what will it become? We will see. But before that, maybe I should also update what is sigma d2 square. That becomes 1 minus K2 squared times the previous prediction error, this much. So this improvement is telling me that we are multiplying with 1 minus 1 over 9, which is close to 1 but less than 1, times the previous prediction error, which was 3 over 4 already, as coming from here. So this thing will be evaluated to be 2 over 3. As you see, this is also less than 3 over 4, and they are both, of course, less than 1. So it's decreasing. The prediction error has decreased a little bit further by the second order prediction, but we didn't really find the second order prediction filters yet, filter coefficients yet. So let's do that. We come up with an A2 vector, which is an iterative way of using the previous A1 vector. What was it? You see at the top, it is 1 and 1 over 2, 1 and minus 1 over 2. And then we insert a 0 to the bottom side. And then plus, we say, K2 times, which makes minus 1 over 3 times, because K2 is minus 1 over 3, as we found here. Okay, times the same vector, 1 minus 1 over 2 and 0, in the folded order, which is 0 minus 1 over 2 and 1. So notice the relation between the two. They are just inverse orders of one another. So that's essentially what you do. And then you come up with the first item automatically becomes 1. Notice that the last is 0 and the first is always 1. So when you flip their positions, you come up with a 0 here, and 1 plus 0 will always give you a 1. And here you will have a 0. Here you will have the new coefficient k1 times the new coefficient k2, or kn in general. So the last one will become kn here at the last position. It will start with a 1 and end with a kn. That's the layout that you always come up with. 1 minus 1 over 3 and minus 1 over 3 again. It just happens to be like this. So for a single coefficient linear predictive filter, it was minus 1, it was 1 over 2, sorry. The filter coefficient was 1 over 2. Now we have two coefficients, and the filter coefficients are 1 over 3 and 1 over 3, right? So let's iterate once more. If more autocorrelation values are given to you, then you can iterate even further. We will find K3, that is minus Rx3 minus A2 of 1s times Rx2. What is this A2 of 1? It is this minus 1 over 3, by the way. And then minus A2 of 2, that which is also minus 1 over 3, by the way. This is the first filter coefficient, negative of the filter coefficient. This is the second filter coefficient, negative. So I'm using that one here, times Rx1. You see how I term by term multiply Rx3, Rx2, and Rx1 with this one, and this one, but in a negative way. So there is a minus sign here, here, and here. There are already minus signs in the coefficient signs anyway, like here and here. So we have this in the numerator, and the denominator is again the previous prediction error, which is sigma d2 square. And when you just substitute the values, the numbers inside, it will give you minus 1 over 8, which means the third order prediction filter's third coefficient is equal to negative of this one, which is 1 over 8. Okay. Let me also find the new prediction error, which is 1 minus K3 squared times the previous prediction error. So 1 minus 1 over 16 will be the new scale that will scale the previous prediction error, which was 2 over 3. And this is calculated to be 21 over 32, which is slightly less than 2 over 3, but not much. So as we can see, these autocorrelation values are really poor for predictive coding kind of things. For predictive coding to be successful, let me go up a little bit and let's observe these autocorrelation values. This autocorrelation drop from 1 to 0.5 and then staying, but then 0.5 to 0.25. These are too much of autocorrelation drops. So the relation between the consecutive samples is not really high here. Normally, for example, for real life images, the pixel values of the of two neighboring pixels they have a very strong relation, like 0.95 autocorrelation between two consecutive pixels, or 0.9. So Rx1 is usually 0.9, which automatically makes, if it's an autoregressive 1 sequence, for example, the relation between the first and the second, the first and the third, sorry, pixels are 0.9 times 0.9, which is 0.81. again a large number. So it doesn't really drop such dramatically. This is a relatively poor drop in autocorrelation, and that's why the the prediction error stays quite large still, not decaying very rapidly, and it's not performing very well. Now let's find A3 vector. The vector A3 is composed of the vector A2, which was already 1 minus 1 over 3 minus 1 over 3, and we augment it by 0 to make it size 4, and then we will say it is minus K3 times the folded version of 1 minus 1 over 3 minus 1 over 3, 0, which is 0, minus 1 over 3, minus 1 over 3, and 1. And by the way, minus of K3 is plus 0.8. Sorry, plus 1 over 8 times this, which will give you 1 to be the top, but it's not a filter coefficient. It's just for the calculation purposes. The filter coefficients are negatives of minus 3 over 8, minus 3 over 8, and 1 over 8. Now I'm a little bit confused about whether I should use, no. I have to use, I have to use a minus sign here. It is plus of K. So this is supposed to be like this. Okay. So what can we say about the filter coefficients? The filter coefficients are therefore H1 is equal to 3 over 8, H2 is equal to 3 over 8, and H3 is equal to 1 over 8. So these are the new filter coefficients of the third order filter. Look how they progressed. In the previous case, it was H1 is equal to 1 over 3, and H2 is equal to 1 over 3. In the first step, it was H1 is equal to 1 over 2. So let's put them into boxes. First, we had this first order filter coefficient, which we found out to be 1 over 2 in the optimal sense. But if we use two filter coefficients, they become like this. And if we use three filter coefficients, they become like this. So they are changing their values. Okay, they are being updated. They become longer and they are being updated. So which one are we going to use? It depends on, of course, the monitoring of these prediction errors, squared errors. When you think that they are small enough and the gain is marginal, you can stop there, and there is a systematic way of doing that, which is also another heuristic, also known as the AKK information criterion. And that is something that we found and discussed last week. Okay, so much about this. And by seeing some numerical examples, I am sure you will make better sense of thinking about this kind of a gradual improvement, more beneficial. For example, if we only say that the filter coefficients are third order filter coefficients, and what are they, then you should be dealing with the, let me okay, discuss it from my notes. If you don't want to solve it in a recursive manner, but solve it in a manner that you are using the vector matrix notation, the third order filter determination would be like this. It would be Rx0, Rx1, Rx2, Rx1, Rx0, Rx1, Rx2, Rx1, and Rx0. So you just have to substitute these values, which are given at the top of the question, to you. And these are the filter coefficients H1, H2, H3. And you will say that these will be equal to Rx1, Rx2, and Rx3. So you will have to solve this system of linear equations, linear set of equations. Or you can invert this matrix and multiply it with this vector to find this these filter coefficient vectors. But inversion of a 3 by 3 matrix is usually more difficult than doing 3 iterations from the top to bottom and to find this one. So numerically, actually doing this kind of an iteration is way faster than trying to invert this. Besides, if you are given a 4 by 4 set of equations, then you dump everything that you obtain from solving this equation, and then you draw the 4 by 4 version of this matrix vector multiplication set of equations. And it will be useless. It will become more and more difficult. Whereas using the Levinson recursion, you come up with these results, and you can immediately proceed to the length 4 version using an iteration. And the iterations are very simple. You do this, and then you fold the two vectors like this. You substitute the k value in between, and you come up with the new set of values for the linear filter coefficients. And you are also updating the prediction error, because you will be using this value in the denominator of the next iteration. So that's how it essentially works. Now, so this is how Levinson recursion essentially works. Starting from this, I want to proceed to two-dimensional prediction. Because in 2 dimensions, usually students get confused how to construct the equation and solve, either using the Levinson recursion or by just solving the set of equations that I'm showing you. The example that I will proceed from the top is something like this. Suppose that we are sliding a template of 2 by 2 pixels and sliding over the image, okay, like the convolutional template. And we have this, I think I should write it like this, x of, this is x of, let me make it thinner then. This is x of n m, okay? And n is the row count, m is the column count. So horizontally it's m. So this becomes x n m minus 1. Okay, this becomes x n minus 1 m. And this is x of n minus 1 m minus 1. Now I'm going to use this, and this pixel as the past samples to predict the current sample here. Are they really the past samples? All the top rows are past samples because I am sliding in a raster scan order. Okay, so I'm finishing one line and then going to the one line below and then doing it like this. So in a raster scan order, x of n and m is being executed. So all the rows at the top are actually past samples, and everything to the left or along the same row is also a past sample, again because I'm scanning in the raster scan order from left to right. So yeah, these green labeled pixels are all past samples. What could be a non-past sample? For example, a sample here is a future sample. It's not past. Or anything here, or this one here. It's also a past. It's also a future sample because we did not come there yet. So the past samples are here. They could be here. They could be here, 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 and to the left. To the right of this, or anything towards this direction, they are past samples. I can use them for predicting what is x of n and m. And in 2 dimensions, the relations in the vertical direction as well as the horizontal direction are all available to you. We can find those correlations. How do we do that? We just, for example, horizontally multiply every pair inside the image, multiply their values, and then take and then divide by the number of pairs. So we find their averages, average of the multiplications, horizontal multiplications. That will be horizontal 1 correlation. We can also multiply vertically pairs all throughout the image and then average them. That would give me the correlation in the vertical manner. I can use the correlation of 45 degrees diagonals by multiplying every such pair, and whatever number of multiplications I have, I divide by them to average. I can find this autocorrelation value by multiplying them and then averaging. Multiplying and averaging is a poor man's estimation of finding the autocorrelation. If you are given a set of numbers, you can just average them. Or you can multiply every sample by itself to find Rx of 0, by the way. So let me again come back to this size. Sorry for the scale. But I can say that I can find things like this. R0 is equal to the expected value of x of n m square. This is R0. Then I can find R1. But be careful about what you call R1. That is your notation that you have to always use. As you see, if there are horizontal and vertical correlations, then the correlation matrix will not become a correlation matrix. It will become a tensor. So is this R1? Is it R01 or R10? Is it the horizontal or the vertical correlation I'm talking about? So what I'm telling you is this. You have to make your definition of R1 here. Which are you using? Let's use the horizontal ones. So that's equal to expected value of x of nm times x of n m minus 1. So horizontally multiplied versions, expected value is here. I just assigned it to be like this. You don't have to do that. But it's always wise to choose the nearer correlations to have smaller indices like R1, R2, etc. R2, by the way, I will assign to be the vertical correlation, x of n m times x of n minus 1 m. I'm calling this R2. It's not the leg of 2. There are no the difference, the pixel wise coordinate difference between this and this is not 2, but this is another correlation, so I call it R2. Okay, that's my definition. And then I will use R3 to be the minus 45 degrees diagonal correlation, which is x of n m times x of n minus 1 m minus 1. Okay, so it's the relation, the correlation between these two. Whatever I'm using, I'm rendering these autocorrelation values according to my pivot x and m, and I'm comparing this to its left, to its top, and to its diagonal. If I use this as well, I could use that one for the prediction, and in fact its distance, coordinate-wise different distance to this is quite near, so there's a strong relation. I can use it for prediction purposes. I should then use this kind of another prediction to be, let's say, R4. If you have R0, R1, R2, and R3, those 4 coefficients, then your filter structure will give you the related filter coefficients. For example, whatever is R1, R1 is here. So it will give you H1 to be a coefficient that will multiply this pixel value. Your left neighbor pixel value is multiplied by H1. And then your top neighbor relation coefficient value, H2, will be related to R2. And here it is H3 that multiplies your diagonal neighbor. Let me indicate them. So with this kind of a construction, this pixel, your left pixel, will be multiplied by H1. Your top pixel will be multiplied by H2, and your diagonal pixel will be multiplied by H3. And those accumulations will give you a prediction of the current x of nm. That's how you will predict x of nm, by multiplying this this pixel with H1, this pixel with H2, and this pixel with H3. So it's not one-dimensional, it's not going to the past, but it is just getting some distance away from the current pixel. You can use this pixel, this pixel, this pixel, this. It can be a larger predictive filter that you can use. Okay. And then what you do is essentially from here, you construct this set of equations. It's at the top. It's already at the top. Let me not repeat it again. You have Rx0, you have Rx1, you have Rx2, you have Rx3. You define them to be like this. You substitute into this top equation and solve for it, and you will find H1, H2, and H3. And those H1, H2, and H3 you will use here, here, and here for two-dimensional predictive coding purposes. Okay. This is very critical. I didn't spend a lot of time on this one, but predictive coding is used in 2 ways. The most popularly used in 2 ways. One of them is compression of speech compression. The other one is image compression. And this part is image compression, but we have been doing everything in 1 dimension. So extending such 1-dimensional process to a 2-dimensional case is a little bit problematic sometimes. So that's how it is. And be careful about that. If you did not understand this one, please go through this process again and try to understand how 2-dimensional predictive coding works. or how two-dimensional linear predictive filter determination essentially works. So, is this clear now? I have to ask this question at this point. If you understood how to construct two-dimensional linear predictive filter, it's fine. If you did not, you have to go through this again. As you see, there's a problem about what kind of correlations you are going to use, and the correlations are then ordered like to the left, to the top, to the diagonal, and to the other directions as well. They will be R4, R5, R6, etc. And then you construct the set of equations like this and solve for the filter coefficients. And whichever correlation you used for R1, for example, that will correspond to H1. You used R1 using the diagonal, using the horizontal. So H1 corresponds to the coefficient that will multiply this, etc. Okay. I hope it's clear. It has to be clear. Okay, and now, so I can proceed with another, I will say it an example in 2 dimensions, but it's a nonlinear image predictor. This is a specific example that I'm giving you to show that the linear way of approaching the problems is easy in terms of analytical proofs, optimizations, etc. It's there. But nonlinear predictors are also available to you, and they are usually performing better. And this one is used in JPEG in lossless mode, JPEG LS. There are 2 modes in JPEG. Nowadays they are improving, but there are 2 fundamental modes. One of them is a lossy mode, which is the default one. When you save as JPEG, it is the lossy mode that you use. What was it? You may remember, or you may have some impressions. You split the image into 8 by 8 blocks, and then take the discrete cosine transform, and then quantize them, and then put it in a zigzag manner, use Huffman coding, etc. So that is JPEG, but it's JPEG the lossy. Naturally, there is a lossless mode of JPEG, and in lossless mode of JPEG, they use the so-called LOCO nonlinear predictor. LOCO stands for low cost or low complexity. It is nonlinear, but it has less computational complexity than linear predictors in 2 by 2 mode. It works like this. Just like the example that we see right before, we are going to predict this x. I'm not going to denote any coordinates here. This is x, and this pixel value is a, this pixel value is b, this is c. So according to this a, b, and c, what is the prediction value of x? The local is using a rule-based nonlinear prediction. It is nonlinear because it's rule-based. I'm not multiplying a by a coefficient h1, b by h2, and c by h3 and combining. That would be a linear filter. Instead, the prediction, which is x hat, works like this. It's equal to C. The prediction is immediately C if A is greater than C and B is also greater than C. So it's essentially something like this. The top pixels, these pixels, are both larger than this one. So there seems to be an edge here. These are the large values. There's a line that we have here of large values, and this is a small value. So the edge is decreasing along this direction. So if C is less than A and B it's less than B, then x should also be that smaller one, because it's in the bottom of the hill or the valley. It's at the bottom side of the valley. The bottom side of the valley is here. The top of the valley is here, and there's a decline over there. So we decided like that. It could be like this, or it could be equal to b if both a is greater than b and c is greater than b. Okay, then the valley is vertical in that case. Then x is belonging to the lower valley of this line, where a and c are the heights of the valley, and the other one is a plus c minus b, where we can say else. Then it corresponds to a kind of a diagonal thing. So this a plus c minus b is just an average. The conditions of this or this can be inverted to become positive as well for these. And the else condition will stay the same because we are trying to average a, b, and c. But notice that there is this kind of an approach for the most accurate design of this loco. You have to check the internet and look at. I didn't check. I don't have these in my notes. I'm writing this according to my knowledge and according to how I remember. I may be wrong about this, but these are just conditions, and these are just values of B, C, and A, which is quite nice. Because we are not making any multiplications. We don't multiply with any scale. We are just adding or subtracting like this. I think this one was C plus B minus A or something like that. But yeah, let me write it in a different color. Probably it was like that. C plus B minus A. Okay, something like this. So it has no multiplications, it has no optimizations, nothing. It's just an intuitive way of looking at the problem of making a prediction. So logically, what should be the value of x is the thing that you have to think about, and you just decide accordingly. But it's a nonlinear image predictor, and we don't have any expected value of the error here. We cannot really estimate the sigma d square, because everything is nonlinear. We cannot make an analytical calculation. It works, and when you do that, you will see that this is probably for normal images performing better than this linear predictor that we have for the 2x2 case. So this nonlinear predictor usually works better. Such intuitive way of looking at the prediction phenomenon is very popular. It's also very popular in, it's also a lot used in MPEG, but we will see that later. Over here, the prediction that we will do is not the pixel intensity prediction, but the motion prediction. Like from one frame to another frame, an object is moving. So how much did it move? We will look at how much it moved previously, and we will assume that it will continue to move in that direction. So that will be another prediction. And it's also quite a nonlinear prediction, to be honest. So these are the prediction things. And the last thing that I will mention before giving the break is the quantization of the prediction error, which is a problem. Well, if you have a prediction like this here, a predictor is here, it's using the past samples, and it is subtracting from the current x of n, And what we will have is the prediction error. Let's call it D of n. Okay. And in lossy compression, we know that we have to quantize this because that's what we said, right? It's the prediction or transformation is usually the first part of the compression scheme. The second part is quantization, and the last part is lossless compression. So in between there is quantization. But when you do that, then you fall into a problem. Let's suppose that what you have is u of n here, and from this u of n, you use the prediction of the reconstruction, because you are reconstructing your signal, and you add it, this time not subtract, you don't have a minus sign at the reconstruction stage. You add the prediction to the prediction error. Prediction error plus prediction is the signal itself, and you expect to have here the signal which would be equal to x of n, but I will write it as y of n. And if you do it in this layout, the problem that you will have is the u of n will not be equal to exactly d of n. They will be different, and because of this quantization difference, here in this recursive accumulation of making a prediction and then adding to the prediction error to come up with the original signal will start to fail. The error that you have here will grow and accumulate. So you are accumulating the error, which is growing. You normally want something like this. Whatever this quantization error is, let's say the quantizer error is like u of n is equal to d of n plus a quantization error epsilon of n. This much error is here. You want y of n to be equal to x of n plus the same quantization error. So the quantization error you're doing in between, you want to do this error to affect from x to y, but it doesn't because of this accumulation. The error grows, grows, grows. It diverges, actually. This is a divergent scheme from x to y if you do it like this. So what are we going to do? How can we resolve this problematic situation? Well, what we can do is we can incorporate the quantizer into the prediction loop. We can put it inside the prediction loop in such a way that here the reconstruction uses quantized prediction error, U, as you see, and this prediction is also using the quantized prediction error. Let's make both this one and this one to use U. Okay, not the previously the left-hand part is using D. Okay, so let's have them use the quantization inside the prediction. And that thing is called, historically, it's not the accurate way of saying this, it's called differential pulse code modulation. Pulse code modulation is quantization. Differential pulse code modulation is the differential way of doing it, which is where the prediction is. This is a weak name. DPCM is the abbreviation, by the way. DPCM is the abbreviation. But this differential is telling me that the prediction is only leg 1. So it's using only x of n minus 1. H times x of n minus 1 is subtracted from x of n, first order filter. Then it becomes differential, of course. But in general, it's prediction and predictive coding. So this name is not very much appropriate. But the style is historically first incorporated into DPCM. So you can use this name too. It runs like this. You have x of n, and you are subtracting the prediction. So it's quite similar, but it's to the left-hand side now, as you see. Whereas here, I'm subtracting the prediction at the right-hand side of this schematic layout. Now I'm doing it at the left-hand side because at the right-hand side I'm gonna do something. The prediction error is quantized like this, whatever it is. Now I'm going to use this quantized output to do two things. There's a summation here. If I don't have the summation with another thing, I would have a prediction here. So I'm quantizing and then predicting would be the thing. But I'm going to do one thing, because if I use this thing for prediction, I cannot make a prediction from it. It is the prediction error here, right? I'm making the prediction. By the way, there is a subtraction here. I'm subtracting my prediction from the signal. It is quantized, but even without the quantization, here what I have is a prediction error. Using the prediction error, can you make a prediction? No, the prediction is orthogonalizing your signal. So it can't be used as an input. The prediction error cannot be the input. The input must be the signal. So where is the signal? The signal is now here. First of all, the prediction output is itself the signal. Like this. I added to this is the prediction, it produces the prediction error. The prediction error is added, sorry, the prediction, excuse me. This is the prediction. The prediction is added to the prediction error, the quantized prediction error. So here what I have is essentially something like the accumulation is the addition of this branch, which is the prediction error, and this is the prediction. The quantized prediction error and the prediction are added, which gives me something like the quantized version of x of n. Okay, and I'm using that one for prediction and subtracting again. So this schematic is directly producing u of n, which can be used in the decoder side to produce y of n, which is equal to x hat of n. And that x hat of n, by the way, it would be the same as this x hat of n. I don't think x hat would be a nice name. I'm going to remove this hat business. I'm going to say x prime of n. It's just another variant of x, but it's not x hat. It's x prime of n. So this x prime of n that you make here, if you see that this prediction is the same prediction as this one, you notice that this signal is exactly the same x hat of n, x prime of n as this x prime of n. So what does this make? It makes a quantized version of the input, quantized version of x of n, which is something like x of n plus a quantization error. And that quantization error is the quantization error that makes this. But that's what we already wanted. We wanted y of n to be equal to x of n plus the quantization error. So this overall scheme lets you do that. So although we optimized everything, we found the autocorrelation equations, Levinson recursions, and all those things according to the minimization of this, using this kind of a strategy originally. Once you do that, once you design that, you don't actually use it in that way. You use it with the quantization inside the so-called DPCM strategy, which is given like this. Does it change the optimization? Because we optimize by minimizing the energy of this D. Now, this is U, which has a different energy. So should we really minimize the energy of U? The answer is yes. Of course, from here to here, things change a little bit in terms of optimality, but trying to optimize the overall thing together with the quantizer is a mess. It's a headache. And people just don't do it that way. If you can come up with an optimization strategy to optimize this for the minimization of the energy of U of n or the entropy of U of n, if you wish, that would be even more awesome, then you can literally publish that. Otherwise, it's quite difficult. The overall optimization of this is quite difficult. It's unlike this one, which was very easy. We did it already last week. Okay, we just took the derivative of the energy of this with respect to the filter coefficients, and we found the relation. But if you incorporate the quantizer inside, the relations will be quite messy. So it's very difficult. So what people really do is they optimize according to this and then use it like this. You determine the prediction from here and just insert that predictor here. Okay, so as a matter of fact, that's all I would like to talk about in terms of the predictive coding. I don't know what time it is. It is 10:30. Excellent. So we will continue at 11 o'clock with a different topic. We will start with our new discussion regarding quantizers, which is the optimization of this module over there. It's also very analytical, but before that, we will give some break. So this concludes the prediction and predictive coding discussion. If you have any questions, you can ask now, or you may come up with a collection of questions and you may ask it at the beginning of our lecture, which will start at 11 o'clock at the same place. Okay? So I'm stopping the recording now, and we will give a break until 11 o'clock. See you there. And I will also talk about the exam, okay? At the beginning of the lecture in 11 o'clock.
Okay, see you.
Okay, bye.